Hello, welcome back once again. Today we're going to tackle this monstrous looking integral problem. We have the integral from 0 to 1 of the natural log of the following finite series 1 plus x squared plus all the way to x to the power of 11 whole divided by x dx. Now let us record the sum of the first n term of a geometric series formula, right? We know when we have s is equal to 1 plus, so here we have r plus r squared plus all the way to r raised to the power of n minus 1 and then plus r to the power of n. We know the sum here is given as the first term a into brackets 1 minus the common ratio raised to the power of number of terms and then divided by 1 minus r, provided that r is less than 1, right? So here we're given 1 plus x squared plus all the way to x to the power of 11. So our first term here is going to be 1, right? And into bracket 1 minus common ratio there is x. Raised to the power of number of term is 12. We have 12 terms and then divided by 1 minus x. So therefore, our integral, let's call it I, is going to be equal to the integral from 0 to 1. So we have the natural log of, so that is going to give us 1 minus x to the power of 12 divided by 1 minus x. Then whole divided by x, and then we have our dx. So this is going to be equal to, using one of the properties of logarithm, so this is going to be the integral from 0 to 1 of the natural log of 1 minus x to the power of 12, right, minus the natural log of 1 minus x, and then divided by x, and then we have dx. Now, let us recall the Taylor series expansion for the natural log of 1 minus t. So remember, the natural log of 1 minus t is equal to negative sum as n moves from 1 to infinity of t raised to the power of n divided by n. So for this part where we have x to the power of 12, we replace t with x to the power of 12. So correspondingly, we're going to do that to this one. Therefore, our I is going to be equal to the integral from 0 to 1. So here we're going to have the negative sum as n moves from 1 to infinity. So here we're going to have x to the power of 12n, right? Then divided by n. With this negative sign, this one will be positive sum as n goes from 1 all the way to infinity of x to the power of n divided by n. So don't forget, we have a denominator which is x, and therefore we have dx. So this is going to be equal to, so this is going to be integral from 0 to 1. So we're going to take out the 1 over n term outside. So we're going to have here, this is 1 over n, right? So here we're going to have, into bracket, the negative sum as n goes from 1 to infinity. So x to the power of 12n divided by x, that will be x to the power of 12n minus 1. And here plus, so x to the power of n divided by x will give us x to the power of n minus 1. So here we have dx. So from here, I is equal to, so we have to switch the sum and the integral operators, okay? So here we're going to have the negative sum of 1 over n, then into brackets, so we have to integrate from 0 to 1 of x to the power of 12n minus 1, and also integrate, so let's put the x here and also integrate this from, okay, we have a negative outside, remember there is positive here, so we have to put a negative sign here. So we're going to integrate from 0 to 1 of x to the power of n minus 1. Then dx. So that is easy enough to do, right? So here we have I is equal to negative sum as n. Oh my god. So n goes from 1 to infinity. So n goes from 1 to infinity of 1 over n. So here, so remember, this is going to be x to the power of 12n minus 1 plus 1 divided by 12n minus 1 plus 1. So giving us just 12n. And when you insert the limits of integration, so we're going to have 1 over 12n from here. And then minus here, we're going to have 1 over n, okay? So here, if you take the negative 1 over n inside, so we get the sum as n goes from 1 to infinity. So we're going to have 1 over n squared minus 1 over 12n squared. So, you know, from here, this is just the bezels problem, right? So here I is going to be equal to sum as n goes from 1 to infinity of 1 over n squared minus 1 over 12 sum as n goes from 1 to infinity of 1 over n squared. So this is giving us here the Riemann zeta of 2, which is pi squared over 6 minus 1 over 12 times pi squared over 6 is 1 over, this is pi squared over 72. Now, when you subtract this is same as multiplying this by 12 over 12. We'll get 12 pi squared over 72 minus pi squared over 72. And from here, we get our required solution, which is 11 pi squared divided by 72. And this is our final answer. Thank you for watching. If you enjoyed the video, kindly subscribe. Also like, comment, and share.